So I think we are off to a good start this morning, and this afternoon we're changing up what we've done in the past. Our board, so each of the members of our strategic partnership program have a seat on our board and advise us. And our feedback after last year's event is that the event is wonderful, but we could always use more technical talks. And in the past, we've only had technical talks we've had panel discussions that have a variety of people from industry, government, and academia. But our technical talks have usually been highlights of research that is just going on here at Purdue. Our board had said, that's good, but we'd also like to be able to hear what's going on in industry. We also heard from our faculty that they would love to hear more about what's going on in industry other than what they hear on the panels. So this is the first time in at least 8 years that we've actually put down different tracks. So this track is going to be, the next couple talks are by members of our industry partnership program representing and talking about some of the work that they are doing internally within this area. So it's my honor today to introduce Baiju Patel. Dr. Patel is an Intel fellow with Intel Corporation, over 22 years of experience in security. This is not his first trip to Purdue. We have been very lucky to have him back at different times to talk, to meet with students, to collaborate with faculty. Much of his work has been in operating systems and instruction sets for architectures. He's currently the Chief Security Architect for Intel's Client Computing Group. So welcome back to campus, and we look forward to your talk.
Thanks. So it's not going to be a super technical talk, but it's going to cover lots of topics. So just to level set, right? But it is definitely technical. So let's get that right. I have two roles at Intel. One is an Intel-wide role, which is as a security fellow. All of our business units, products, I need to oversee the kind of things we implement in terms of features, architecture, all of that. But the second part is I also exclusively focus on our PC and client division where, the buck will stop with me. So I want to start this for the young people here, right? And not the people my age or even older, right? And I want to tell you, first of all, why I do this. And maybe that's how you want to think about. And it goes back to, I think it was like 8-9 years ago. That time our CEO, Paul Otolini, was giving a talk. And somebody asked him a question. I don't remember the question, but I remember the answer. It's a good answer, right? So his answer was simply this, that look, we do all these things because we have a responsibility to our shareholders. That's obvious, right? And our employees. But there is a bigger reason we do what we do at Intel. And what he said at that time was that, and some of you might think it's exaggeration, and that's fine, but world runs on Intel. If you look at all the servers, data center, cloud, even from your phone, when you click a button, somewhere an Intel server delivers something to you, right? The economy runs on Intel in some ways. And therefore, it's our obligation not only to the shareholders or employees, but it's to everyone else. We cannot screw up, right? So that's a big responsibility. I have a small part of that responsibility. I at least want to make sure that we provide the right security capabilities in products we produce that allows everybody to use what we produce and actually manage the risk of their business. So that's what makes me want to continue to work. That's what keeps me awake at night, but that's what keeps me excited at morning. But this is the kind of things you need to think about, is that what we do, it's not just money. There is a higher purpose, especially in security, because guess what? We are on the right side of the divide, right? And by the way, I am optimist. I actually don't ask the question even, have we lost the war or are we losing the war? I definitely know we are not losing the war. I don't know if we are winning or not. Because we are all here. And the world keeps spinning round and round. So we have not lost the war. That's a good thing. Let's keep it that way. And maybe we can even win. Right? So that's what keeps me going, just as a little background. So the first point is, right, how do I even think about security? So this is my view. I think a lot of people share that. Some people have different views. My view is security is all about risk management. There is no such thing as secure, or there is no such thing as everybody needs this much security. Everyone based on their usage. And I think somebody in panel talked about it, that you need to take a system view. In their environment, in their business, in their day-to-day activity, they are willing to take certain risk to get certain things done, right? So security is simply about risk management. The interesting thing about that is when you work for a company like Intel, what does it translate to? What do you do when you wake up in the morning and you want to think about, okay, now what do I do? It's about risk management. And the fundamental thing about risk management is people use multiple ways of managing risk, from contracts to networks to operating systems to anti-malware software to employee training. Right? There's so many things people deal with in managing risk. Insurance. We are providing one ingredient of that. But the moment the cost of us providing the technology gets anywhere close to the risk they want to manage, they will just opt out. Right? It's not worth it. So we need to constantly look to say, how do we provide security technology that fits this broad customer base's risk profile? And how do we deliver that so they all can manage the risk for their needs, right? It's not one size fits all. Our products go in airplanes, to laptops, to all kinds of things, right? And we need to build this. So what I'm going to walk you through now is it's a very broad stroke view of all the different things we touch in security. It's not just thinking network or firewall or operating system, but how do we build this foundation that everybody can rely on to do what they need to do at the risk they can want to manage and the cost they can afford. Right? That's the fundamental principle. And everything I talk about will sort of talk about that. So just one little more thing about why security, then I get into the technical stuff, right? So first is, right, people want to do stuff. And to do that stuff, they want certain level of comfort, safety, whatever, right? So we want to support those usages. And that's all we need to do. If people can actually use what we produce with the safety, we won. We're good, right? The second part is, for a company like Intel, we are not in charity. We are actually in the business of making money, and we need to survive, right? So it's also the brand promise. People expect certain level of security from us. And that's like non-negotiable, right? So you have to do that, as well as you have to think about usages. And if you're lucky, and I really say that seriously, in our business, if you're lucky, we even make money on security. Most of the times, it's just an expectations. We don't monetize security because it's, as I said, it's an obligation. We got to do it. But sometimes we do make money, right? But this is how we think about security, almost in that order. If people use it, that's great, and therefore they will trust us. That's even better, and we can even make extra money. Super cool, right? That's how we think about it. That's how everything I do fits into the scheme of things. So now let's get into a little more technical stuff, right? So far it was all fluff. So this is one view of how the computing world works. And if you really think about this view, right, somewhere at the bottom, I like to think it's CPU because, that's what we produce, right? So I have to think that way or I'm just, But on top of it, we have BIOS and firmware. This is the first thing that runs. You have operating systems and hypervisors and things like that. You have OS and you have applications. So if you really think about it that way, I see a lot of work out there where people really look at this and say, I can improve the security of operating system, or I can do some things about improving security of programs and all that. And actually, that's what mostly I'll talk about today because that's the time I have. But there is a different world out there too. And our products, and many of you products you use as well as produce, have this view as well. But you might have multiple CPUs, they're connected to a network, there is storage where data sits, there are different types of memory, you might even have accelerators like graphics or FPGA or a machine learning thing. And as you secure this part of the world, think about it, and then you put it here. And now you think about it and the data not only processed here, it goes here, it goes here, it gets stored here. It sits even in the memory or it gets there. If these things around the CPU, if they don't have comparable security to what I delivered here, did I really do a good job, right? So when we think about security, we think this, we think that. And some of those we actually leave it to the rest of the world to figure out, like large part of network security. We know how to really kind of deal with it. But there are parts where we spend a lot more time because that becomes part of system architecture. Today, with the time, I'll just talk here. Sounds good? So I'm going to use a bunch of pictures to just walk you through. So now that I established that, at least in my world, security is the center of, CPU is the center of universe, why don't we start with that? So if you think about CPU, we want to like to think that our customers want to know that the software, that very first software that runs, is quote unquote trusted. How do you do that? First instruction. So we have sort of mechanisms we build here in the CPU to say, can I verify the initial part of the code is actually trusted? Now, the code comes from OEMs, people who build your laptops or servers or whoever, but they want to know that it's their signed code, right? So we bring the code, we put it in the cache, we make it non-evictable, all kinds of things. We check the signature. Only if everything fits, we say, OK, proceed. So that's how the CPU part of the world starts. If you don't do that, then you have a fundamental question to ask. If you don't even trust the beginning of the compute on a CPU, can you trust anything else? So it kind of becomes a foundation. This is one way of thinking about it, by the way. There is another way too, I'll talk in a minute. But once you get that, then you can say, OK, I can check the signatures of the rest of the BIOS, and you get to the OS loader, which loads the OS, and that's signed by OSVs, and you build the whole chain of trust. And now you know all the code you run is actually signed, you know where it came from. Now here is a question, right? Just because it's signed doesn't mean it's good, right? I mean, if you write a check and you just sign it, but you have no money in account, it's not good, right? Same thing happens here. If it is a buggy code, old version, revoked, updated, whatever, it still has good signature. And when the CPU is starting this early in the game, there is no way of knowing if something was revoked or anything, because you don't have rest of the infrastructure up. You don't have operating system, you don't have connectivity, you have nothing, right? So that's not enough. And people like to think that I want to actually record what happened. So later on, I can check to make sure that indeed not only it was signed, but it has the versions, it has the properties I wanted, right? So we look at building this entire infrastructure. We keep measuring the components all the way. We record it in this device called TPM. And now you can even later on tell if you started with a solid foundation. And then you can seal secrets to these measurements and all that, so that if anything got compromised or changed, keys don't become available and things like that. But that's how we build it, right? That's one way of thinking. But this is where it gets interesting. Because we have so many customers, different people think differently. So here is a different view. And this is actually a challenging one. This we did before we did the previous slide. So it's not in a chronological order, but it's in an order where I can explain you things. So what this says is, you know what? There are so many people who make laptops and servers and all that. Who the hell knows what they do? So many of them might not have the smart graduates from here or wherever, right? And it might be buggy. So can we actually say that all of this code that ran before operating system, let's put it outside the trust boundary? There are two problems with this. One is, think about my customer. We tell them, I'm going to build a technology because people don't trust you. And they look at it and say, what do you mean? You know, he bought a Dell machine. It's the brand promise, right? What do you mean they don't trust me, right? They don't want anybody to think that they are not trusted. So it creates a challenge because we have different customers. But we provide a technology because there are different people who need different things. And in that case, you can say you execute a set of instructions. It cleans out the state of the CPU and everything, brings it to the right point, and starts new measurements from hypervisor or OS. And now you can say, I don't have to trust all of this as much because I started later. That has not been as successful. And the reality is, the reason it has not been successful goes back to risk. That a lot of people look and say, you know, I buy this machine, I pay money for it, they stand by it, do I need to go through all this, right? So people don't necessarily want to put extra effort that they don't need to only in one narrow aspect of security. So we have this technology since 2006. It's limited success. And it's gaining traction, but we have it. It's actually a fairly complex thing to do. Because think about it, right? You want to actually reset the counter in a way and start all over again after the system is set up. So we need to check for memory aliases and all kinds of things. But that's how we do it. So now the system has started. At some point you got to operating system. That's now the highest privilege code running on the machine until we get to the next slide. But then what you're trying to do is, if this is the most valuable part of the system, We want to protect it from here because that's what you use to interact with the rest of the world. That's where all the problems are going to come in from. So what kind of things we do? Now the things you have studied in computer architecture, yeah, sure. You have memory protection, you have page tables, you might even use segmentation if you really want to torture yourself. But there were fundamental deficiencies in these architectures. And I think about it, I like bang my head to the wall saying, why did it take me so long to realize? But I'll give you a simple thing we did here that made world of a difference. So the simple privilege concept is, right, kernel can do whatever apps can do. Kernel is higher privileged than app. App executes app code. So our architecture is kernel can also execute app code. Now app code inherently is not trusted. Why anybody in right mind want to execute app code with kernel privileges? Guess what? People are very smart. Anti-malware vendors at times were doing that, just that. Finally, we shut all that down, but we added a capability to say, no, the hardware CPU will prevent any execution of application code with kernel privileges. And it was because if you overwrite a function pointer, jump to user mode code, which is malware, boom, game over, right? This is an interesting part. That was easy, actually, very simple to do. We said, okay, why can't we do that for data? Why should kernel attack data from the user mode? But guess what? Kernel has to attack user mode data because you need to do I/O and other things, right? Even paging. It has to have access. So what we did was we created a bounding box that only certain APIs with certain on and off, you can say, now I want to copy data, you copy, you sanitize it, do that. That did not become as successful because in case of Linux, it got used, but in Windows, they didn't have a single part of code that copied data. So some things become easier, some things become harder, but these things are universally used. And the irony of it is, right, all of these machines actually use this, but I bet most of you don't even know, right? This is how we don't make money. Going back to the earlier point. So as we do OS and all this stuff, something else happened. And actually the interesting thing about this picture is that its history goes back to here. We were doing this, and we said, while we are doing it, can we sneak in virtualization in there because someday it will be useful? And all the business guys said, no, because people will buy fewer servers. You virtualize a server, you put a bunch of machines instead of that in VM, we lose business. But we did that anyway. That has been, in my opinion, one of the most successful security technology in Intel processors because guess what? Everything in cloud is that. It's even there on clients, right? So this became fundamentally very important. And the way you have to think about it, and there are 3-4 files I'll build up to walk you through it, is that how we think about a much broader picture than a typical research paper or a vertical industry will think. So in this kind of things, what you're trying to say is, look, these are the guys who manage the machine and you run a bunch of guest OSs. So you want to protect this green stuff from red. That's how I pick those colors, right? That's a no-brainer. And if you have multiple guest OSs, one might be Bank of America, other one might be General Motors, we want to keep them separate. So we built so that this has full access to this, but not other way, right? That worked out great. That's what cloud uses. But people are smart. And this is where we think, we spend a lot of time thinking through all these things and think about how people might use it because we don't control what people do with their processors. The joke at Intel is, right, you have 10,000 monkeys sitting in front of keyboard writing code. We don't know what they will do, but we got to do the right thing. So that's how we think. So this is a different approach to security using virtualization. A lot of Windows clients actually use it. But I changed the colors. What they're saying is the OS itself might get compromised. No matter how hard we try, bad guys will get to it. Can we actually take the security credentials from here and move it to a small OS that's designed for security so that even if the OS was compromised, as long as hypervisor is good, your credentials are good, your Kerberos tokens are protected, your single sign-on, all of that, right? And then you look at it and say, wow, I got that done. While I am added, can I do more? So instead of thinking that this cannot get to that, we are saying this can actually use hypervisor to protect pages belonging to the operating system that you don't want attacker to modify, right? Now you got something else. It's a completely opposite model of what we had. Guess what? We did not have to do hardware design. It was just there. It was just a question of how you write software. This is what we try to do as we think about how we build things, right? And this even gets better in a minute. But the other part that happened in this part is that everybody thought, okay, we are virtualizing CPU. So now you are at it, right? You're virtualizing, you're getting good at it. You say, I'm going to also virtualize devices. Why not, right? Why should I have synthetic devices? I just have a device directly attached to a VM. So we have IOMMU and we designed VTD and all that. You know what the first use was? Security. What people said was, if a graphics card is compromised, it can DMA into any part of the memory. Should it? Is that a good security? No. Okay, let's set up the page table for the device so it can't get to any of that. And suddenly you have a security value. And it was done even in pre-boot time by times, and you just shut off all these DMAs and you say, okay, now I have a good world, right? So as we design these things, we look at it, and you should do that too as you go out in the industry, get a real job, right? That how do I do this so that I can actually facilitate many, many usages as opposed to one narrow thing that comes to my mind. But that was a very interesting thing, and we argued about it, that which one will really happen. But the best way to sell it was to say we virtualize devices, but a bunch of us knew it's a security thing too, right? So these are the two pictures, and I kind of use the colors in a way to just show the contrast, right? That what we were saying was green was trusted, these are not trusted in the top, classic virtualization. We come here, previous slide, now the OS you do your work on is not as trusted, and the security OS is trusted. But then what happened? Then Snowden came about, and the insider attacks became real. And the way cloud providers looked at it and said, we are losing business. Some of our customers don't want to host with us because they're worried that our government or somebody else will ask us to give their data, and we have to, or one of our disgruntled employees. So we changed this model to say, oh wow, none of this can be trusted, because the guy who is running this doesn't want to trust them because they might not trust your government or whatever, right? And this is something that we're spending a lot of time right now solving, because we have to do this without breaking this or this. This is what people use. This is what the world is running on right now as you introduce this, which are the fundamental assumptions that these are trusted on the same machine. We need to support this, right? So this is how it plays out in our world in how we think about security. So, are we done, right? I mean, is this a fundamental question? How far can you go? So we looked and said, okay, let's just think about the isolation and look at the full picture. And essentially you end up with three things, right? And this is where I introduced the last concept on this line of thinking. When you have virtualization, you can have a bunch of guest OSs and you can isolate them from each other, right? I said Bank of America to General Motors. Perfect, great, works, right? This is the oldest thing we have sort of. We have processes, and operating system keeps every process separate and all that. That's your process isolation. And we looked at it and said, in a process, in so many threads, in shared memory, is everything equal? The answer is obviously no, right? And so we introduced this concept of SGX, and that we call sub-app isolation. So if you know the right part of your app that you want to protect at a different level from everything else that working with shared memory and all that, you carve that out, you put it in this environment, and it basically is, quote unquote, protected from everything outside. But naturally, it's hard to program, it's not as scalable, it is a lot worse performance, so you need to make some smart decisions. The moment you go down that path, a lot of people don't want to do hard work, they want to ship a product. So these kind of things take a lot longer to adopt, and you can see that in the marketplace. So, I think I'll skip this part. I think most of you know what ROP, JOP, and all that is, but one of the things we are introducing here for protecting software, because everywhere still it's a C code and other things that run. So we are adding shadow stack and things like that in our architecture so that you can protect the shadow stack and the return addresses from that, and therefore prevent this class of attacks. What I really find most intriguing about this kind of attacks is it's like, it looks like a duck, it quacks like a duck, it must be a duck. It runs from the program memory, it has all the privileges of program memory, it looks like instructions, but it's an attack code, right? So it's very, very hard to detect. And detecting is not an answer typically for ROP. And that's why we had to go through extra effort to add shadow stack and other things. So I'm going to finish in next 2 minutes, maybe 3 minutes, so that we can have some time for whatever questions. The other part that was extremely important in all this is crypto, right? And the way we did crypto was a very different approach from classic thinking. Classic thinking will be, I'll build an engine for AES, and then people can send workload to it, results come out. In our world, in general purpose computing, that doesn't work well because there's a lot of overhead back and forth. When you send it to the crypto engine, the CPU goes in low power state or schedule something else. By the time you come back, wake up, no gains, right? So we instead broke up AES instruction and broke it down into parts and said, you can implement any flavor of AES you want. And frankly, it's not a security technology. But it's one of the most successful security technology. Why? It delivered the performance for encryption. So when you go to Facebook and you get HTTPS, it's quite likely that there is somewhere AES and an instruction executing to deliver the thing to you. You do VPN, all of these. Because performance was a barrier to cryptography. We addressed that, and we did not just do it for AES, but we did it for PKI. There are other instructions for Galois field multiplication, things like that. There's a long list of things. But instead of thinking security here, we thought differently. We thought, can we make this usable at a cost that people can afford? Because servers cost real money. The disk encryption using AES costs real battery life. Can we make it efficient so people use it? Because if people use it, it will improve security. That's it. So it's a very, very different approach from what we talked about. Same thing we did with random number generator. And the way we enabled random number generator is most unique because my nightmare is 7 years after I shipped a CPU, what if it didn't generate random number? I mean, what are we going to do? Somebody bought the thing expecting it to work. How do you predict the future? So we said that random number generators should seed with what we produce, and they should collect all of the entropies anyway. So even if we didn't generate as good a random number, at least you had what you had before, right? But this is how we think about security for how we deliver it to the world because people count on us, right? So I'll just do this and then I'll stop. The last part that ends up being is that as I do all of this, I need to think about it that, okay, network, we have fairly good handle. Storage, everybody's encrypting. Can we do a better job? Yeah, sure, whatever. But then we are adding all these accelerators, graphics, to machine learning, to FPGA and all that. And we are actively looking at architectures here to say we need to deliver comparable security from here to here. We need to protect the links. We need to protect the communication. So this ends up being a bigger and bigger picture that companies like Intel and a lot of our peers end up working on. And that's a small part of what we contribute to cybersecurity. The question is, are we done if we do that? Right? Or are there bigger problems we need to solve? Like, cloud guys, as I'm doing virtualization, they're moving to function as a service. Okay, what the hell am I going to do when now so many functions, they go all over the place? How do I deliver security? Is that the right answer? Quantum computing, right? All these things keep coming up. Instead of CPU root of trust, think about a platform root of trust. Because now there are all these smart components. If I have full trust in this, but this one started with bad firmware, did I lose, right? So these are all the things we work on. The hard part about working for Intel is this is the stuff that's really interesting that I can't tell you about right now. So with that, thank you very much. I don't know if I have time for questions or not, but I'm around for a little
We
bit.
do have a few minutes. The microphone is back over here.
I'll leave this so that you can think about, are we done yet?
Baiju, you talked a little bit about the hardware and the software partitioning for security, like AES. So in Intel, how do you make this decision when some software technique should be in software or security technique should be in software or should be burnt into the silicon? And how do you price that kind of an innovation?
Yeah, so AES is actually a very good example. So we looked at both the options. And the classic way of thinking is, let's just build a hardware block, right? It's a real problem to build a hardware block in a CPU because every core, do you put one? So as we grow to the number of cores, how many do you have? If you share them, how do you make sure the context is clean? If you put it in far side of the CPU, there's a lot of communication delay, synchronization, right? So dedicated accelerator was hard to build. Instructions were relatively easy to do, and then we can microcode to make existing hardware work nicely. But then there was a problem. My security friends are very upset. This is not secure, right? So sometimes the biggest problem with security at Intel is the security guys, because nothing is good enough for them. And then you look and say, okay, you get nothing if you try to do an accelerator, and we have experimented with accelerators where the performance goes down instead of improves because you're trying to accelerate 64 bytes of encryption. I mean, it's more overhead to just farm it out and bring it. So you argue and you discuss, and then somebody puts foot down and they survive or not. But it's not a fun process. Or the other way of saying it, with great difficulty. That's how you get gray hair.
Touching again on the security versus performance aspect, it seems like Meltdown and Spectre were like root caused by you guys trying to like squeeze out as much performance as possible. How do you balance out like the security versus performance there? Because it seems like the mitigations for those problems ended up costing like more performance than any benefits that could
So
come.
I'm going to answer the question without really talking about those two, because I work for Intel and it's complicated. But the point always is, right, at the end of the day, it goes back to risk management. If we stop delivering performance, people will buy something else, even our competition's product. So at the end of the day, performance is a number that people can figure out I got more or less. Security, some people have talked about getting numbers, but it's not that way. So performance does matter. And frankly, if we actually were aware that something like this can happen, we would have done things like that, because we don't take that kind of risks. None of our customers, none of our academic friends, nobody told us or pointed out that, by the way, I think you should look there. And life was good. But there are smart people, and it's a foot race. The trick is always, are you going to respond? Are you going to own it? And are you going to fix it? And are you willing to take temporary setbacks? Not only for us, but our industry partners. And they were all willing to work with us to do that. And yes, we gave up some performance, but we will be in a better place. So all in all, it's a good thing. It got us something straight. Now we are always thinking about it. And go ahead.
Thank you for coming.
Absolutely.
The question I have is about, with ever finer tolerances on the chip, the real estate's getting so dense, are things like row hammering a harbinger of the future? Could you comment on row hammering and what that might mean?
So rowhammer is an interesting one, right? That's another very creative attack, just like ROP or side channels, right? These are all very smart things people do. And it's very hard to tell what will happen where, right? But we do different techniques, like even on a memory bus, for example, we run the data through a LFSR to try to equalize the number of zeros and ones to minimize side effect and things like that. You probably don't know it, but we do that. We are adding memory encryption, so with encryption, we will get a lot more equalization. Internally, it's a bit harder, but there are places where we add error checking bits and other things. But actually knowing exactly what it will be is very hard. So smart people at Intel come up and say, why don't we do this? And we look at it and see if we can afford to do it. So we constantly keep evolving it, but it's very hard to tell. It's like black swan, right? What other people will find. But if you guys find it, we'll fix it.
Is that a function of denser real estate, or am I on the wrong track there?
I mean, when I took my VLSI class in 1984, we were talking about metal migration, right? Stuff can happen in chips all the time. And I don't know if I'm not a silicon technologist. I can't really answer that question. That's my friends that do that. And it's actually, this time, it's not I can't tell you, I don't know it. Right? Fair enough?
Yes, sir. And
Okay.
there's a site, was it rowhammer.com or something if you want?
Say it again?
There's a site called rowhammer.com, I think it's called.
Okay.
Stuff about rowhammering.
Thanks.
Quick question. I mean, I love this idea that it's about risk analysis, risk management.
Yes.
But kind of in classic risk analysis, we might think, for those of us who were here last year, you think about what would happen to this, what would happen to this building in the event of a tornado? And what's the response to that? How do we deal with that? And, what's your risk? Well, there's this idea that there's some probability that a tornado will hit and then some probability that things could, the windows could break out if that happened. But when you're dealing particularly with hardware, you might say, okay, there's a probability that we'll discover some attack on this hardware, but it doesn't mean that, okay, and then that attack might happen someplace. It's, if that attack occurs, it could happen every place.
Correct.
Does that fundamentally change how you do risk management from kind of classic ideas?
No, so the fact is, right, bad things can happen and they will happen, right? And they have happened even to us, right? I mean, going back to FDiv, right? So as much as we can think of, we really try to make sure we don't want to have a recall. That can break the company. So we go at extreme lengths to try to make sure those things don't happen. Every once in a while, there are challenges. But the good thing is that industry wants to make sure all this runs. And what we really appreciate is our partners, right? Operating system vendors to cloud providers to OEMs. They're willing to work with us to find software and hardware combination to get around whatever happens. And Spectre and Meltdown is a good example of that, right? People took hit because it's important to their business, it's important to our business. We are in this together. And as long as we understand and have that level of collaboration, life is good. But if our customers or partners said, end of the day, it's just your problem, everybody will hurt. And we really appreciate them not thinking that way. Because otherwise it's just predicting the future, right? But we take it very, very seriously. We have to. There's no choice.
And with that, we'll wrap up this talk. Thank you very much, Baiju. Always
you
great
so
to have
much.
that campus. We'll take a 5-minute break and we'll come back with the next technical talk at that time.